Hello viewers, my name is Dr. V. Kishen Ajay Kumar, Department of ECE, IARE Engineering College, Hyderabad. Today's topic is two point sources with equal amplitude and opposite phase, and the other topic is multiplication pattern. So these are the two topics which we are going to discuss today. Let us start our session. Here in the earlier session, we have discussed about the arrays of two point sources with equal amplitude and spacing. Two point sources, if there are 2 point sources here, these 2 point sources are placed midway between the origin, and these are both are having same equal amplitude and phase. These both point sources are having equal amplitude and phase. So in the second case, we are going to discuss about if this point source 1 is shifted to the origin. If this point source 1 is shifted to the origin O, then what will be the electric field strength due to these 2 point sources? So we are going to derive the expression based upon this, that the point source is shifted to the origin. So let us discuss today that here you can see here 1 in the display, 1 and 2 represent the 2 point sources, that is point source 1 and point source 2. Here you can see here that the point source 1 is located with respect to the origin on the x-axis, and here the total distance at a distance point P, we are going to calculate the electric field strength due to the combination of these 2 point sources 1 and 2 at a distant point P. So if the reference point in figure, the shown figure is shifted to source A1 instead of midway of array, then the amplitude of the field pattern remains the same. That means example 2E0. So 2E0 represents the amplitude of the electric field strength due to the 2 point sources. But the phase pattern changes as shown below. But the phase pattern changes as shown below. So you can see here the path distance between the path that is 1 and 2 dash, it is represented as d cos theta. So here there are draw two lines parallel from point source 1 and point source 2. So in these directions, draw 2 parallel lines from 1 and 2, and you draw a perpendicular line from 2 dash to 2. So join 2 dash and 2. So 2 dash and 2 represents the perpendicular from 2 dash to 2 to the x-axis. So if we want to calculate this distance, that is 1 and 2 dash, so you will get d cos theta. So by applying the trigonometry function cos theta, you will get the distance as 1, 2 dash. And the distance between the 2 point sources is represented as d. The distance between the 2 point sources is represented as small d. Here, let us calculate the resultant field strength. That means here there are 2 types of field strength. That is, one field strength is produced from point source 1. The other field strength is produced from the point source 2. And the resultant field pattern, it is nothing but the electric field strength produced by the electric field patterns produced by the 2 point sources, that is 1 and 2. So you can see here in the equation, E is equal to E1 e power J0 plus E2 e power J psi. Here, point 1, that is the point source 1, is located at the origin. At the point source P1, it is located at the origin. Any plane wave equation is represented as E1 e power J psi. Any plane wave equation, the electric field strength, it is represented as e power J psi. So here E1 represents the amplitude. As we have located the point source 1 exactly at the origin, the phase angle becomes 0. Hence, from the point source 1, the electric field strength produced by the point source 1, it is given as E1 e power J0. Similarly, the point source P2, the electric field strength produced by the point source P2, it is given by E2 e power J psi. So we are not writing here the psi function as 0. You can see in the equation that the psi function, that is the phase angle function, is not represented as 0. Why? Because the point P2 is not located on the origin, but point P1 is located on the origin. Hence, we have written the phase angle between the point 1 and point 2 as 0. That is, E is equal to the resultant field strength is given by the combination of E is equal to E1 plus E2. That means the field strengths produced by the 2 point sources. Let us say the two field strengths produced by B1 and E2. The resultant field pattern is given by E is equal to E1 e power J0 plus E2 e power Jsi. So if you take in this equation E1 as common, if we take E1 as common, you will get E1 plus E2 e power Jsi. Why? Because e power J0 is equal to 1. E power J0 is equal to 1. So e power J0 is equal to 1. So we have ignored this term e power J0 here. And the remaining terms have been written here as E1 plus E2 e power Jsi. And already we know that psi, the phase angle, it is given by the function beta d cos theta. So we know that psi, the phase angle between any 2 point sources, is given as beta d cos theta. Beta represents the propagation constant, that is 2 pi by lambda, and also d represents the distance between any 2 point sources. D cos theta represents the path difference. So d is the distance between the 2 point sources, and d cos theta represents the path difference or phase angle or the path difference between the 2 point sources, that is d cos theta. So equations from the above equations 4 and 5, let us assume here the two amplitudes of the 2 point sources be equal. That means E1 is equal to E2 is equal to E0, let us say. Here we are going to derive the equation based upon that we are going to consider these 2 point sources are going to produce a phase of opposite phase pattern and also the same amplitude. So we are going to consider 2 point sources with equal amplitude, and same phase. But the only change here is we are going to shift the point source one to the origin. So if we shift the point source to origin, we will get this equation. And let us assume E1 is equal to E2 is equal to E0. If we substitute this E1 is equal to E2 is equal to E0 in this equation, we will get E0 into 1 plus e power Jsi. E0 into 1 plus e power Jsi. So mathematically, by simplifying this expression, we can also simplify further e power Jsi as e power minus Jsi by 2 plus e power Jsi by 2. So we can take e power Jsi by 2 as common. And if we multiply this, the function which is in the brackets with e power Jsi by 2, you will get this function, that is 1. Right? So if we multiply the equation, that is e power minus Jsi by 2 plus e power Jsi by 2 with e power Jsi by 2, you will get the function 1, that is e is equal to E0 into 1 plus e power Jsi. So in order to reduce the function into trigonometric function in terms of either sine or cos, so we have simplified this mathematical expression 1 in this way. Now, if we divide this by 2 into, if we divide this equation, the numerator and denominator with 2, so we will get here 2 E0 e power Jsi by 2 into e power Jsi by 2 plus e power minus Jsi by 2 by 2. So we are going to multiply the numerator and denominator by 2, and if we take e power Jsi by 2 as common, you will get this equation. And we know that this equation represents cos theta by 2. This equation, according to the trigonometric functions and trigonometric formula, we know that e power x plus e power minus x by 2 is equal to cos x. E power x plus e power minus x is equal to cos x. So as there is e power x by 2 plus e power minus x by 2, we are getting here as cos psi by 2 function. So 2 E0 into e power j psi by 2 into cos psi by 2. You can see here E is equal to 2 E0 represents the amplitude here. 2 E0 represents the amplitude. We can also normalize this 2 E0 as by taking the function as 1. So if we want to normalize the resultant field strength, we shall assume that the E0 is equal to 1 by 2. We can assume here the E0 as 1 by 2. Or we can also indirectly specify 2 E0 is equal to 1. So if we want to normalize the resultant field strength, we are going to assume the total amplitude as 1. So E is equal to 2 E0 into e power j psi by 2 cos psi by 2. So here the first term represents the amplitude, the second term represents the phase function. That means cos psi by 2 e power j psi by 2 represents the phase and 2 E0 represents the amplitude. So as we are going to normalize 2 E naught is equal to 1, we have written here as E norm. So E norm represents the normalization of a resultant field pattern produced by the 2 point sources. So this is given by cos psi by 2 e power j psi by 2. So cos psi by 2 into e power j psi by 2. So this is the equation which represents arrays of 2 point sources of equal amplitude and space when the point source 1 is shifted to the origin. And again, further simplification, this cos e power j psi by 2, we know that e power j theta is equal to cos theta plus j sin theta. We know that cos theta, e power j theta is equal to cos theta plus j sin theta. So from that trigonometric formula, you can also reduce this simplification, that is e power j psi by 2 can be rewritten as cos psi by 2 plus j sin psi by 2. Cos psi by 2 plus j sin psi by 2. And further, if we apply this is in the rectangular form. If we want to convert this rectangular form into polar form, we can write this as cos square theta plus sin square theta. That is cos square psi by 2 plus sin square psi by 2, which is equal to 1 into tan inverse of b by a. Into, so we represent this as cos square, you can see here, cos square theta plus sin square theta into tan inverse of b by a. Tan inverse of b by a means sin psi by 2 by cos psi by 2. So sin psi by 2 divided by cos psi by 2 represents tan psi by 2. Represents tan psi by 2. Right? So tan psi by 2, and here tan inverse of tan psi by 2 is equal to psi by 2. This is written here. So tan inverse of tan psi by 2 is equal to psi by 2. So this we have represented as angle psi by 2. Angle psi by 2. And we know that cos square theta plus sin square theta is equal to 1. So cos square psi by 2 plus sin square psi by 2 is equal to 1. So we represent this normalized electric field pattern of 2 point sources as cos psi angle psi by 2, which is denoted in the polar form. Now let us see to the next case 2, that is the arrays of 2 point sources with equal amplitude and opposite phase. So taking the electric field strength equation from the earlier session, that means we have already derived the expression of arrays of 2 point sources with equal amplitude and equal phase. So from there, we are going to find out the resultant. We are going to take the equation, that is the resultant field pattern, that is E. So E is equal to E1 e power minus j psi by 2 plus E2 e power j psi by 2. Here, this is exactly similar to the above concept, except that the point source 1 is out of phase with respect to the source 2. So here the title opposite phase, it represents that point source 1 is exactly out of phase at an angle of 180 degrees to the source 2. That means when there is a maximum output in source 1 at one particular instant, then there will be a minimum field or minimum radiation pattern in source 2 at that instant and vice versa. That means due to point source 1, if the radiation pattern is maximum, then at the same time at source 2, the radiation pattern will be minimum. So under these conditions, we are going to determine the electric field strength with opposite phase and equal amplitude based upon 2 point sources. Here, with referring to the figure 1, that means this is the figure we have denoted here. This is the point source 1 and this is the point source P2. And from this P1, we are going to get E1. And from this P2, we are going to get E2. That means the electric field produced by P1 is E1. The electric field produced by P2 is E2. So the total resultant field pattern is given by E is equal to minus E1 e power minus j psi by 2 plus E2 e power j psi by 2. So you can see here, as these 2 point sources are out of phase, we are going to represent, that is the point source 1 as minus sign. So here the minus sign, minus E1, indicates that point source 1 is out of phase at an angle of 180 degrees with respect to the point source 2. So because phase of source 1 and source 2 distance point is minus psi by 2 and psi by 2, since the reference being at between the midway of 2 point sources. Right? So the resultant field pattern is given by minus E1 plus E2. And again, similarly, let us assume the amplitudes of the 2 point sources to be same. That means let us assume E1 is equal to E2 is equal to E0. E1 is equal to E2 is equal to E0. So if we substitute this E naught value in this expression, that is E1 is equal to E2 is equal to E naught. So we'll get E is equal to minus E naught e power minus j psi by 2 plus E naught e power j psi by 2. So if we take E naught as common, you will get e power j psi by 2 plus e power minus j psi by 2. So you can see here, if we take E naught as common, we will get e power j psi by 2 minus e power minus j psi by 2 by 2j. And further, to convert this electric field strength into trigonometric function, let us multiply the numerator and denominator by 2j. Let us multiply the numerator and denominator by with this function, that is 2j here and 2j here. So this total function becomes a sine function according to the trigonometric formula, that is sine psi by 2. So we know that e power x minus e power minus x by 2 is equal to sine x by 2j is equal to sine x. So this is one of the trigonometric formula. If we apply this trigonometric formula, this mathematical function can be simplified as E is equal to 2j E naught sine psi by 2. E is equal to 2j E naught sine psi by 2. So we know that psi is equal to, that is the phase angle is equal to beta d cos theta. Psi is equal to beta d cos theta by 2. What is beta? So beta is the propagation constant represented as beta is equal to 2 pi by lambda. So beta is equal to 2 pi by lambda. So let us assume these 2 point sources, the distance between the 2 point sources are lambda by 2. That means here there is one point source P1, there is another point source P2, and let us assume these 2 point sources, the distance is taken as lambda by 2, and d is equal to lambda by 2, and beta is equal to 2 pi by lambda. Beta is equal to 2 pi by lambda. Right? So if we substitute these two, let us see what happens to the electric field strength produced. So let d is equal to 90 degrees, let d is equal to lambda by 2, and 2 E naught j is equal to 1, and E is equal to 2j E naught sin beta d by 2 into cos theta, we know already. And if we substitute these two, that is beta d cos theta, if we simplify this, beta d, so we will get 2 pi by lambda into lambda by 2. So if we substitute these two, you will get 2 to cancel, you will get pi cos theta. So you will get pi cos theta. So here this by 2, hence we have written here as pi by 2 cos theta. Right? So here beta d by 2 is equal to pi by 2, you will get. Here beta d by 2 is equal to, you will get pi by 2 cos theta. That means we are going to normalize this function as by assuming 2 E naught is equal to 1. 2 E naught is equal to 1. That means the amplitude is taken as 2 E naught is equal to 1. 2j E naught is equal to 1. And at the same time, if we substitute the value of beta and d in the electric field strength, we will get the normalized resultant field pattern, which is given as sine of pi by 2 cos theta. Now let us find out the maximum in order to draw the radiation pattern. If we want to draw the radiation pattern of 2 point sources of equal amplitude and opposite phases, so we need to find out in which direction the radiation pattern is maximum, and in which direction the radiation pattern is minimum, and in which direction the half power points distribution is located. That means the half power point angle distribution are distributed in which direction we need to find out. That means HPPD, maxima and minima, these three we need to find out to draw the radiation pattern between the 2 point sources. Now let us find out the maximum direction, in which direction the radiation pattern will be maximum. So as we already know, the E norm, that is the normalized electric field strength, is given by sine of pi by 2 cos theta. We know that the normalized electric field pattern is given by, in the previous derivation you can see here, E norm is given as pi by 2 cos theta. E norm is given as pi by 2 cos theta. So we will take this function. We will take this function to calculate the maximum and minimum radiation field strength. So we know that if we want to find out the maximum strength, that means E will be maximum. The electric field strength E norm will be maximum when this sine function is maximum. Right? So when E is maximum, then this sine function will be maximum. And when this sine function will be maximum, when the value of theta is equal to 1. The maximum value of a sine function is 1. So we already know the maximum value of the sine function is plus or minus 1. Plus or minus 1 in both the directions. So, in order to find out the maximum value of this normalized electric field strength, let us find out the solution by applying some trigonometric solution. That means sine of pi by 2 cos theta is equal to plus or minus 1. So we know that the maximum value of sine function is 1. The maximum value of sine function is 1. And in both the directions, there is a possibility that the radiation pattern will be directed. The radiation pattern will be in the plus 1 direction and also in the minus 1 direction. It may be in the 90 degrees direction, it may also be in the minus 90 degrees direction. It may be in the 180 degrees direction, or it may also be in the minus 180 degrees direction. So for this function, that is sine of pi by 2 cos theta is equal to plus or minus 1. So for this function, if we find out the trigonometric solution, you will get pi by 2 cos theta max is equal to plus or minus 2n plus 1 into pi by 2. So this is the trigonometric solution given for the sine function. Here we are going to find out the value of theta max. Hence we have indicated the suffix as max here. We are going to find out the maximum direction. Hence we have modified cos theta as cos theta max. Cos theta max. So from this equation, pi by 2 cos theta max is equal to plus or minus 2n plus 1 into pi by 2. So here both sides pi by 2 is there. So pi by 2 and pi by 2 get cancelled here. And the remaining terms are cos theta max is equal to plus or minus 2n plus 1 into plus or minus 2n plus 1. Now let us assume this n value as 0. Let us assume this n value as 0. So if we substitute this n value as 0, the remaining term is 1. That is plus or minus 1. So cos theta max will be equivalent to plus or minus 1. Cos theta max will be equivalent to plus or minus 1. So for this function, the theta max will be 0 degrees and 180 degrees. Right? Cos theta max is equal to plus or minus 1. So theta max will be equal to cos inverse of plus 1 and cos inverse of minus 1. So theta max will be in two directions, that is cos inverse of plus 1 and cos inverse of minus 1. So which are equivalent to 0 degrees and 180 degrees. So which are equivalent to 0 degrees and 180 degrees. So here we are getting the value of theta max. We are going to get the value of theta max as 0 degrees and 180 degrees. It means that if we represent the radiation pattern like this. So this is suppose if we represent here this as 0, this as 90, this is 270, sorry 180, this is 90, and this is 180, and this is 270, and this is 360 degrees. So we have seen that the theta max value is 0 degrees and 180 degrees. That means the radiation pattern will be maximum in this 0 direction and also 180 degrees direction. Right? So the radiation pattern will be maximum in two different directions, that is in 0 degrees direction and 180 degrees direction. Now let us find out in which direction the radiation pattern will be minimum. So to find out the minimum direction, we should take again the same function of electric field strength, that is E norm is equal to sine of pi by 2 cos theta. So we know that E norm, that is normalized electric field strength, is equal to sine of pi by 2 cos theta. So from this basic function, we are going to find out the minimum direction. So to find out the minimum direction, so that means the electric field strength will be minimum when sine function is minimum. Also we know that the sine function will be minimum, the minimum value of sine function is 0. So based upon this concept, we can write this sine of pi by 2 cos theta will be minimum at 0. That means the sine of pi by 2 cos theta will be equal to 0. Now the trigonometric solution for this sine function is equal to 0 is given by pi by 2 cos theta min is equal to plus or minus n pi. So this is the trigonometric solution for the sine function if it is 0. And also as we are going to find out the minimum direction, and this cos theta has been modified as cos theta min. That means the radiation pattern in minimum direction, this has been specified as theta min. Theta min specified the minimum angle of direction. The minimum angle of direction, that is the radiation pattern is directed. So if we substitute pi by 2, if we simplify further pi by 2 and pi, you will get cos theta min is equal to 0. you will get cos theta min is equal to 0. Right? So here, if n is equal to 0, substitute n is equal to 0. If n is equal to 0, if we simplify this function, you will get cos theta min is equal to 0. That means theta min is equal to 90 and minus 90. Theta min is equal to minus 90 and 90 and minus 90. So what does it mean here? The minima radiation pattern will be in the directions of 90 and minus 90. That means if you draw a diagram diagrammatically, you can represent this as 180 and 270. That means in this direction, the radiation pattern will be minimum. In the direction of 90 and minus 90, the radiation pattern will be minimum. Now let us find out the half power point distribution. That means if the radiation pattern is like this, from here the radiation pattern will be at what angle? The radiation pattern, that means exactly half of the maximum radiation field of the major lobe is known as HPPD. HPPD. Or we can also simply call it as half power beam width. So half power beam width or half power point distribution, let us find out. That means the maximum amount of power exactly at half of the major lobe. The maximum power distribution exactly at half of the major lobe is known as half power beam width. At half power points of the major lobe is drawn as a half power point distribution or half power beam width. Let us discuss is half power point. So we know that the half power point distribution, the E norm, that is the sine of sine function, will be equivalent to minus 1 by plus or minus 1 by root 2. Plus or minus 1 by root 2. That means for this sine function is equal to plus or minus 1 by root 2. So we need to find out the trigonometric solution, which is given by pi by 2 cos theta HPPD is equal to plus or minus 2n plus 1 into pi by 4. So plus or minus 2n plus 1 into pi by 4. So if we substitute in this function n is equal to 0, if we substitute n is equal to 0, so you will get pi by 2 cos theta HPPD is equal to plus or minus pi by 4 if n is equal to 0. If we further simplify this function pi by 4 and here pi by 2, you get cancel here. If we substitute n is equal to 0, you will get cos theta HPPD is equal to plus or minus 1 by 2. Cos theta HPPD is equal to plus or minus 1 by 2. So from this function, cos inverse of plus or minus half, we know that it is 60 degrees and 120 degrees. So cos inverse of plus half and cos inverse of minus half is equivalent to 60 degrees and plus or minus 120 degrees. Here we have calculated the maximum field strength, that is the maximum directions of pattern and minimum direction of pattern, and also half power point distribution. So based upon these three values, now we are going to draw the radiation pattern for arrays of 2 point sources with equal amplitude and opposite phase. So we got here, if you draw a figure, we know that the maximum points are located at 0 and 180 and the minimum points are located at 90 and minus 90, and half power point distribution is located at 60, 120. 60, 120. So based upon this values, we can draw the radiation pattern like this. That means it is maximum here. That is 0 and 180, and this is 90. And the minima, that is the minima directions will be in the direction of 90 and minus 90. This is minima. And half power point distribution are at an angle of 60 and 120. We can draw here like this 60. This is 60 and 120 here. So this is 60 minus 60. This is plus 60. And this is 120. This is minus 120. And this is minus 60. So like this, you can draw the radiation pattern for arrays of 2 point sources. If we find out the resultant field strength, that is the E is equal to sine of pi by 2 cos theta. From this function, we have drawn the radiation pattern. Now let us see another case, a similar case, arrays of 2 point sources with unequal amplitude and any phase. So case 1 represents equal amplitude and same phase, and case 2 represents same amplitude and out of phase, and case 3 represents unequal amplitude and any phase. That means arrays of 2 point sources of unequal amplitude and any phase. So let us consider a general condition in which the amplitudes of 2 point sources are not equal. That means any phase difference, say alpha. the phase difference between the 2 point sources, let us assume is as alpha. Now with reference to the figure already shown, let us also assume that source 1 is taken as reference for phase, and amplitudes of fields due to source 1 and source 2 at a distance point is E1 and E2, which is E1 greater than E2. So as we are going to consider unequal amplitude, we are going to consider here as E1 is greater than E2. That means the point source P1 is producing an electric field strength of E1, and point source P2 is producing the electric field strength of E2 in such a way that point source 1 is producing a larger amount of radiation pattern than P2. That means E1 is greater than E2. This is our assumption in this case. As E1 is greater than E2, there will be some small phase difference between these two electromagnetic fields distributions. That is, let us say phase difference as alpha. Now the total phase difference between the radiations of these 2 point sources is given by psi is equal to beta d cos theta plus alpha. So here an extra parameter is added here. So generally the phase angle, this equation represents psi is equal to beta d cos theta only for equal amplitude and phase, or equal amplitude and out of phase. We represent the phase angle as beta d cos theta. But as we are going to consider the case unequal amplitude in any phase, we are going to add an extra parameter phase difference, which is represented as alpha. That is psi is equal to beta d cos theta plus alpha. So alpha is the phase angle by which current in I2 of source 2 leads the current I1 of source 1. So this is the case we have represented here, 1 and 2. Let us assume here as 1. The 1 is located at the origin. That is, the point source 1 is located at the origin. And here 2 is a point source. And there is a phase difference between these two as alpha. Between these two radiation patterns produced by the electric field by the point source 1 and point source 2. There is a phase difference of alpha. And there is the angle is phase angle is represented as beta d cos theta plus alpha. Now the total field pattern is given by E is equal to E1 e power. Generally it is written as e power j psi. So E is equal to E1 e power j psi plus E2 e power j psi. So as we have seen here, the point source 1 is located at origin. The point source 1 is located at the origin. Hence we have denoted this psi function as 0. So hence this value becomes 1. E power j 0 is equal to 1. So we have written 1 as here, E2. And let us take E1 as common. If we take E1 as common, 1 plus E2 by E1 e power j psi. And let us assume this E2 by E1 as k. E2 by E1 as some constant factor as k. And E is equal to E1 into we can represent it as 1 plus k into e power j psi, where k is equal to E2 by E1. We are going to assume just an assumption, k is equal to E2 by E1, and E1 is greater than E2. E1 is greater than E2, and k is less than 1. So k lies between the values of 0 and 1. So this is the electric field strength produced by 2 point sources with unequal amplitude in any phase, which is represented as E is equal to E1 into 1 plus k e power j psi. So we can also further extend by simplifying this above expression by applying some trigonometric formulae. That is, we are going to take the modulus for the above function. So for this function, E is equal to E1 into 1 plus k e power j psi, we apply modulus on both sides. If we apply modulus on both sides, what will happen? We will see. Modulus of 1 plus k e power j psi, we are going to apply modulus for this function. We will see here. E1 into 1 plus k into e power j psi means we can write as cos psi plus j sin psi. We know that e power j psi represents cos psi plus j sin psi. And if we simplify, that means if we further simplify this expression by multiplying with k, you will get 1 plus k cos psi plus jk sin psi. So 1 plus k cos psi plus kj sin psi. So we are going to write in the form of a plus jb. So we know that from the trigonometry, a plus jb. So from the modulus of a plus jb, we know that from the trigonometry formula, that is a plus jb is equal to root of a square plus b square. We know that from the trigonometric formula, a plus jb, modulus of a plus jb is equal to root of a square plus b square. If we apply this trigonometric property, you will get 1 plus k cos psi whole square plus k sin psi whole square. So this is the real part. 1 plus k cos is the real part, and j k sin psi, it is the imaginary part. J k sin psi, it is the imaginary part. So from the taking the real and imaginary parts outside, you will get the root of a square plus b square. You will get root of a square plus d square. So here psi represents the phase angle at point P. Psi represents the phase angle at point P. So you know that root of a square plus b square at angle psi. And if we want to convert this into some polar form, you will get root of a square plus b square at an angle psi. That means the tan inverse of tan psi. So if we represent this as A, if we represent this as B, according to the according to the conversion of polar form, you know that tan inverse of B by A. The formula is tan inverse of B by A. So what is B here? B here is k sin psi, and A here is 1 plus k cos psi. So B represents the k sin psi, and A represents 1 plus k cos psi. If we substitute these two equations in tan inverse of B by A, you will get psi is equal to tan inverse of k sin psi by 1 plus k cos psi. 1 plus k cos psi. So we are assuming this total function as some function as pi, unless we have denoted this pi as angle pi here in the equation 15. So the total function, that is tan inverse of k sin psi by 1 plus k cos psi is equal to pi, and this pi is represented in equation 50 as angle pi. You can see here angle pi here. So the total field strength produced by two point sources with unequal amplitude and any phase is given by E is equal to E1 into 1 plus k into cos psi plus j sin psi, or simply E is equal to E1 into root of 1 plus k cos psi whole square plus k sin psi whole square at an angle psi. At an angle psi. So this is the arrays of two point sources with unequal amplitude and any phase. So let us discuss. Let us recap what we have seen today. So we have seen the arrays of two point sources with the equal amplitude and phase, also with unequal amplitude and any phase, and also the unequal amplitude and unequal phase. So unequal amplitude, that means any amplitude and any phase. So these are the three different cases we have seen today. Let us see what is the multiplication pattern. So let us apply the two point sources of equal amplitude and spacing multiplication pattern. So in the previous case that we have discussed three cases to draw the radiation pattern. To draw the radiation pattern, we have discussed three cases. That means we have, based upon the trigonometric formula and some mathematical analysis, so we have derived some expression of total field strength produced by the two point sources P1 and P2. That is E norm is equal to 2j E naught sine of pi by 2 cos theta. So this is what we have seen here, sine of pi by 2 cos theta here. So this is the function through mathematical analysis we have derived this function 2j E naught into sine of pi by 2 cos theta. So after deriving the expression of E norm, so we have further simplified to find out the maximum amount of direction, maximum direction of radiation pattern, and minimum direction of the radiation pattern, and also the half power point distribution. So based upon all these, after finding all these values, based upon all these values, we are going to draw the radiation pattern produced by the two point sources. But in this new concept, that is the multiplication pattern, so we need not do any mathematical analysis. We need not do any mathematical analysis to draw the radiation pattern. So just by inspection, we can draw the radiation pattern of any number of sources. That means whether it may be 2 point sources or 4 point sources or 6 point sources or 8 point sources, we can draw the radiation pattern just by inspection. That means we need not do any mathematical analysis as how we have done the mathematical simplification of to find out the electric field strength produced by the 2 point sources. Now let us find out some equation for the multiplication pattern considering the 2 point sources. So let us consider here two short dipoles which are superimposed over the two isotropic point sources and are separated by a distance. So you can see in the display here, there are two short dipoles here, You can see here, this is a dipole here. And these two dipoles are superimposed over the isotropic point sources separated by a distance of d. Separated by a distance of d. It means that we are going to consider two point sources which are having isotropic, means which are having the equal distribution in all directions. So isotropic point source, it is one, it distributes equally in all directions like this. And also we have considered the one dipole here. Here we have considered one dipole here. For this dipole, the radiation pattern will not be like the point source. So for this dipole, the radiation pattern will not be similar to the point source. But we have combined. That means a dipole and the point source have been combined here. A dipole radiation pattern will be like this. A dipole radiation pattern will be horizontal. That means here the radiation pattern is horizontal for a dipole. And if you take a point source which is superimposed on this dipole, the radiation pattern will be like this in all different directions. So these two, that is, we have combined two sources here. We have combined two sources collectively. That means a point source is superimposed on a dipole, and here also a dipole is superimposed on the point source here. So by doing so, let us assume the field pattern of each isotropic point source is given by E naught is equal to E1 sin theta. So E naught is equal to E1 sin theta. So here, if the radiation pattern, so we know that the sin theta function will be like this. The sin theta function will be like this. So if the radiation pattern, if we take the sin theta, the function E naught is equal to E1 sin theta, the radiation pattern will be like this from these two point sources. Suppose if the radiation pattern is vertical, here the radiation pattern is horizontal. Suppose if we consider the radiation pattern to be vertical like this, then in that case we assume E naught as cos function, that is cos theta. Right? So E naught is equal to E1 sin theta. We can take any two expressions, any of the above two equations. That is, we can take E naught is equal to E1 sin theta. We can also take E naught is equal to E1 cos theta. So it depends upon how you place the antennas with respect to the ground. That means whether you are going to place the point source on the dipole with respect to the ground, it is vertical or horizontal. It is vertical or horizontal. Suppose you have placed here horizontal. You can see here, you have placed like this, it is horizontal. So this is horizontal with respect to the ground. So the radiation pattern will be like this. The radiation pattern will be like this. So if the radiation pattern is like this, that means it is vertical. Then the radiation pattern is sine function. The radiation pattern will be sine function. And if the radiation pattern, if we place this dipole as in this way, the radiation pattern will be like this. So to obtain the radiation pattern like this, to obtain the radiation pattern as shown in the figure B, we need to take cos function. We need to take the cos function. So let us discuss this about multiplication pattern in the next for the next lecture. Right. So here we have discussed earlier the three different cases of isotropic sources of equal amplitude and same phase, equal amplitude and opposite phase, and any amplitude and any phase. So these are three cases. Based upon the three cases, we have drawn the radiation pattern, and let us discuss the multiplication pattern in detail in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.